Hey everyone, and welcome back to the Information Bottleneck. And today we have a great guest, Christian, an AI researcher. He has a long history in AI and deep learning. He co-invented Inception and Batch Normalization. He co-founded xAI, and then he left to found the Math Inc. and here he is. Hi, Christian. How are you?
Hey, it's my pleasure to talking to you. Happy to be on your podcast.
Thanks for coming. And as always, Ellen, hey Ellen.
Nice to see you, Ravid, and nice to meet you, Christian. It is a real honor.
Thank you.
So today we'll talk about different topics, including like how to build a frontier lab and what does it mean in specifically in math and like what we actually think about AI and math and how we see the future. So let's start with uh, um, xAI, right? Like you co-founded xAI, I think it was like 3 years ago, right?
Yes.
Something like that. So let's focus. I want to focus in I think the interesting question, like how you actually build a frontier lab, like what types of people and what types of directions and paths you need in order to build organization that at the end will make a great model.
Yes, I would more like consider myself as a founding scientist or a founding engineer than a co-founder. Really, Elon was doing like most of the like organization, and he was the CEO, and he's basically drove the whole company in a sense, and also maybe Igor and Jimmy were helping much more than I did, and so yeah, I think. Also, another remark that Elon would hate this notion of lab. He didn't think of xAI as a lab. He thought of it as more like an entity that drives engineering and and creates the best AI in the world and helps accomplishing a lot of other engineering goals. So I don't think so every lab is different or every entity is different, and it's very different from, let's say, what Jan LeCun has started or what Anthropic is or how OpenAI started. All of them were very unique in their own ways. So I think there is no real pattern there. So I think what xAI really needed, or we tried to achieve in the early days, is to get people around that had a proven track record, knew what they did, already had like experience with various technologies that like language models and training and large scale use of GPUs. So it was an extremely small circle of technical members, like 12 people for a year, who used initially 5,000-ish, then more like at the end, like when I left, like more than 100,000 GPUs, but closer to 200. So, and it was a very small amount of people using a huge amount of compute. So you had to be very deliberate in what you are doing and how you are spending these insane resources. So that's one issue. So basically, we didn't take any chances of hiring people who didn't have a proven track record of being able to utilize that compute and make a good use of it. So that was
But
very important.
But how does it start? Like, do you write on the board like we need people like in these like people that know to pre-train and people that like know this topic and this topic and this topic, or like
Yeah.
we just want like talented people that they will figure it out how to train a frontier model.
Yeah, we had definitely people who were hired for a reason, and most of us were hired for a reason. And some, for example, we had like engineers who were hired from DeepMind who did like a lot of pre-training and they knew the ins and outs. So Igor was, for example, pretty much involved in a lot of pre-training effort in various models. Uh, so So yeah, we have a lot of people who were hired for particular reasons, and I mean, as Elon says, so basically you need different skills at the beginning of the company. So you have to create like the foundations for your models, so collecting the data, training the initial models, getting together the infrastructure, all that work, and that's you needed people for that reason, and we hired several good people who did like amazing infrastructure work, or some people were very knowledgeable about data centers. So yeah, I mean, so in the beginning, Frontier Labs that are like a startup that is planned to be scaled to a huge size, or like huge compute, it needs to be very deliberate on getting the right skill set together.
And how do you like manage, that like that now like we don't have anything, right? But like there is some really really far goal, and like and how you manage this trade-off, right? Like between like decide what is good for, I don't know, the next version of the model that it's probably really bad, like we want it to be like the best model out there in a year from now.
I mean, that's definitely nobody would think of that we will do a bad model or anything like that. And actually, I think it's like Elon is more principled in that sense that he had like very clear vision of understanding what intelligent explosion will mean, and he's still like more forward looking than most other places. So a lot of other big companies say, okay, we have to invest in AI, let's spend this much $1 billion, and Elon says that I need this and this because this is required for that and that. So he has a clear dependency graph in his head, and then he says, okay, if AI will be big and we don't do it, then we'll have to pay a lot of money to the competition, so let's not do that. Let's try to build it on our own. And then he finds a way of scaffolding the whole thing and get to a point where it's competitive, and also then it satisfies his needs. So I think Elon puts all the different stories together in his head, and he understood that AI is the basis for a lot of other technologies, and that's why he built the lab. But in the meantime, he had to get investments. So basically, he had to say, okay, we produce this, we produce that, we demonstrate skills here, we have user numbers, etc. Because otherwise, it's hard to get funding.
So I want to shift a little bit, much as I love this discussion, to auto-formalization in Mathematics Inc. Let's start with, I guess, Gauss. He completed, or sorry, it completed, should be gendering, completed the strong prime number theorem formalization in 3 weeks after human experts stalled for, I think it was 18 months. Where exactly did the humans get stuck that Gauss didn't? And what was it, like complex analysis components or like search strategy? And
Yeah.
also, what do you think this reveals about the comparative advantages of like AI formalization versus human formalization?
Yeah, I mean, okay, so the actual story is that this was a long-standing effort by Alex Kontorovich and Terry Tao, who were trying to prove some version of the prime number theorem. The strongest form of the prime number theorem is the Riemann hypothesis. So that's that would be a great thing if we could solve. I mean, we don't have the proof, but this proof is like known for like 130 years. But basically, the story was that they used a lot of students, or like they worked with a lot of students to that they gave out the work to them, and they did a lot of the actual link coding, and then they worked for a year, and they estimated they didn't get stuck. They estimated that, okay, the Borel-Theodori theorem would take another year or something like that, or maybe a half a year, but generally a lot of time. And they said, okay, that was enough so far. So we have proven this theorem modulo the Borel-Theodori theorem, and then we had to. That's a complex analysis theorem. So and yeah, and then we were looking into that, and then that was a good test bed of saying, okay, can we do it faster? So we worked with Jared Lichtman, who was at Stanford, and he basically created a blueprint for it, and we started to hand feed that blueprint to the Gauss system and finished it in about 2 weeks. So which is pretty impressive, but this was still a lot of human effort involved. So we had to. So Jared found like various subtle bugs in the textbooks that proved that theorems, and then they had to be fixed. So basically, it turned out that the theorem was somewhat more technical than it looked. So it required, for example, not just like in other proofs, you have like 1 epsilon and delta, and then we had to basically introduce like 3 other radii that depended on each other, etc. And it basically that math had to be also kind of figured out. So it was not like just formalizing the theorem. But basically, I think that the cool thing was that we started the original version of the Gauss system. Actually, it was not mathing back then. It was this whole effort started at Morphlabs, which was Jesse's company, and it's more like an infrastructure company. But when I left xAI, I told Jesse that I leave xAI if we are doing this formalization project together. And he said that, yes, let's pivot. And he diverted a lot of his resources and attention to this project. And basically our first formalization attempt proved 2,000 lines of, basically created a 2,000 lines of formalization. This next the prime, that was a simplified version of the ABC theorem, some relatively early result by De Broglie from the 60s. That was not even published. It was more like a folklore result for a while. And then that was 2,000 lines of link code created semi-automatically, but much faster than humans would do that work. And then Jared didn't know much lean, so he could do it. So we had Jared who knew mathematics, and we had students who knew lean to some extent, but not very much, and mostly just using AI.
But let's go a step back a bit. Like, why you think, like, I don't know, like formalism, like, what does it even mean, formalism, and why it's important?
Yeah, I mean, that's a good question. So actually, I think formalization is an overloaded term. So a lot of people think that mathematics as seen in the textbooks is formal mathematics. Like that's what normal people would think, oh, that looks so complicated and a lot of formulas, so it's formal. So people use formal in that sense. But what we mean by formal mathematics is basically that we turn mathematics into a computer code. And it can be written in some language. That language can be like there are various languages for that purpose, and the latest language is Lean. And people like that language more because it's a bit more elegant. So it has a more elegant syntax and higher abstraction levels than previous formalization languages. But it's essentially the same task as writing a computer code, just much more complicated because you need a very deep mathematical understanding to use that system. So it takes much longer to write 100 lines of lean formalization than 100 lines of C code for some relatively like well-known programming task. And so so basically formal mathematics is this turning mathematics into this programming language. It's much more verbose than, let's say, a normal paper. So for example, this ABC theorem, like it's a simplified ABC theorem that took it was like a page, 1.5 page paper, but it was 2,000 lines of lean code when it got formalized. So it was much, much more verbose than the human proof. So when you formalize something, it's kind of the same level of details that you have to go into as if when you write a computer code. You can explain to me in 3 sentences what you want to code up, and then you spend like 3 weeks on coding it. So the similar thing is with lean. And the advantage of that is that once you have it, you can just ask the lean compiler, verify this proof for me. And it doesn't need any AI. It's just completely mechanistic. And then it will tell you 100% certainty that your proof is correct. So there is no more error left for to discuss. I mean, unless the lean has a bug. But generally, the only bug that might remain is in the formalization of the statement itself, but its proof will be 100% guaranteed. So that's a big deal because one of the scarce resources for reinforcement learning in AI is verifiable problems. So one of the problems of like saying like frontier math, like a benchmark, and then say, okay, solve this problem, mathematical problem, and then the AI spits out some text, and then a mathematician has to read it, or like he doesn't understand, and another mathematician, and then they might discuss it for weeks and decide, okay, that might be correct, or it's roughly correct, or it's a bit, it has some holes, but it's essentially correct, or it has a subtle bug. So it's much harder to get to a closure, even for a single theorem. It happened on various latest attempts on solving problems that people discussed for weeks whether the computer-generated solution was correct. If it's in lean, then there is no more discussion. Then the proof is correct. You might not understand the proof because it's very abstract, but it's correct.
So related to that, you had that ProofBridge paper, which has joint embeddings aligning like the natural language and the lean proof pairs. But how sensitive is that to like distribution shifts across mathematical subfields? So like, I didn't look exactly at all of the training data, but I assume you didn't get every mathematical subfield, right? And so does a model trained primarily on like analysis proofs transfer to combinatorics or algebra, or does each domain require its own like embedding space, or maybe even further like set of data?
Yeah, I personally not on that paper, so I don't really know the exact like. But yeah, I like that paper, but I don't know the exact details. So I assume it's. Actually, I was sketching up some similar ideas already in 2019 in my auto-formalization as a frontier for xAI. So that was my paper. So that's basically promising to pass toward general artificial intelligence. So that's basically. I think it's. So this aligning embeddings, I think it's a nice thing if you do it because you have less resources than you cannot train like large language models because you don't have enough compute. So then that might be helpful and might be accelerating the overall research or like making the auto-formalization much more like efficient in terms of compute. But a lot of this auto-formalization today is just made by just agentic AI, where you are just using some frontier language model and you don't need this kind of bridges, to be honest. Probably it will be a good idea in the long run. I don't really know how sensitive is it to out of domain generalization questions. So I have no idea.
So do you think like, okay, so let's assume that you learn the model like to be really good in math formalizations. Does it useful to do you think it's useful to other fields like both kind of the model itself, but also like the methods and the thing that we can learn from it?
So could you repeat the question?
Like, do you think that now, like, model that you're trying to be expert on lean and like to be very good in formalization, do you think it can like you can use the same methods in other fields that I don't know if they're related, even like coding, right? Like, do you think there is some ability between these fields?
Yeah, it's hard to say definitive statements. The measurements are all over the place, but there is a general agreement that, especially what we found in early reasoning models that were trained on informal mathematics, like solving informal mathematical, not lean, but informal math, definitely helped coding abilities. So basically, there is transition. So basically, you have generalization from informal math to coding. So I assume that if you have an extremely sophisticated system that does lean, is basically probably helps programming, but I don't think anybody did that experiment. So generally, I don't see lean as a prime capability or like any of the formalities. So that's not my goal. Is basically it's more like, so there are two goals for formalization. So two main purpose that you can that it can have. One purpose is create a scaffolding at which you can start addressing more and more complicated mathematics without any human feedback. So you can say, okay, if my lean is really good, then I can go to more and more frontier math and start solving problems that no human has solved, and still verify them and not wait for like years for humans to verify those results. So it's like it accelerates things like 100 or 1000x. The second thing I think for lean is important is basically this kind of like, it can become kind of like the assembler language of all of reasoning. And because mathematics is not just mathematics, so I think when mathematics will start to become like cheap and easy to get, it's like, as Terry said, like generating ideas now is super cheap. But I would say even just doing and creating a completely new mathematical field will be like very cheap, like a few $100 maybe. And then at that point you can devise mathematics for various particular specialized purposes in various domains like biology or physics or computer special areas of computer science that were not mathematized yet, because first of all we are just, humans are too slow, etc. And then we can basically create like whole mathematizations of topics that were not mathematized yet, and we have much more guarantees of correctness. So for example, AI is not mathematized yet, and we could get much better foundations for AI if we create the right math, and that right math might be developed by AI, not by us. And that's
But do you think like we can do it for all the field? Like we can like describe all the fields with math?
No, not all the fields. I mean, we don't necessarily need mathematics to tell whether. So if you do self-driving and you want to recognize a street sign, then you don't really need like a mathematical theory for that. But you might discover rules that make the models much more robust than they don't. Then these rules, these mathematical methods will help us to create, let's say, more robust self-driving systems, because then the AI will be used to build those AI systems. So I think, of course, the particular application of like saying, which route should I take to get to a certain point on the map, there is mathematics behind it, but not that particular question is mathematically interesting. The mathematically interesting is, okay, how do I find the shortest path, or how do I look up something quickly, etc. And those things can be addressed mathematically, and I think that will be a big thing, because now we can create math very quickly, and we will be generating much more efficient algorithms much more quickly, and those algorithms will be verified. Not like the code we generate right now is not really trustworthy at all. So all these vibe-coded programs are kind of nice to some extent, and they work to some extent, but they have their drawbacks.
But do you think like what does it mean trust in this in this case? Because like at the end, right, I want to build like kind of a website or whatever, some app, right? What does it mean? It really depends at the end, the usability of this app is really depends on the user itself. So how you can even think to formalize it in some sense?
You can still formalize a lot of like aspects. You can ask the same question: why do you verify like chips or whatever? You verify chips because they go through a long optimization process, and during the optimization process, small things might break. So the human specifies the chip, and at the end of the optimization, your chip might do something else that the human wanted in the beginning. So that's already one important thing to verify. The second thing is that there are definitely important aspects of every code that you don't want to happen. So for example, you don't want to crash with a memory error or a segmentation fault or whatever. Or you don't want, there are various kind of injection attacks that you don't want to happen ever, or you don't want to access certain memory, or you want to say that if a user initiates a certain transaction, it never will cause certain part of your database change, or all those things can be basically, all those properties could be extracted by an AI and then formulated mathematically, and these invariants could be kept through the overall development process. So currently, if your AI, maybe your application works, and then you ask your AI to refactor your code, and then it changes 10,000 lines, and then who knows what it broke. So we definitely, it's much more dangerous than in chip design, where the tools were developed with like extreme scrutiny, and they say, okay, we make sure that there is no bugs, and there are thousands of unit tests and other tests, and then still you have bugs, and still you break your chip, but the verifiers catch those mistakes at the end, so you don't tape out another Pentium with a floating point bug. So that's basically for code. It's even worse now because our tools that optimize the code are super brittle. They're like much higher probability of introducing errors. So it's basically guaranteed at this point. So that's something we need to fix, and that's why I think. But these, like these websites or whatever, these vulnerabilities are one thing. I think what the real other interesting thing is algorithms that rely on more mathematical insights, and there are surprisingly many areas where you actually have like a clever algorithm at the core, and you want to prove that clever algorithm works, or it has the certain characteristics, like it's fast enough, it doesn't consume certain memory above a certain amount, etc. And those things, I mean, this was traditionally the work of computer scientists, but even every single problem that people thought about took like years to refine gradually over and over, like publishing papers about that algorithm, like slightly better and better. And now this could be done automatically.
So, related to that, I've seen from like your mission statement, and I think you had some public announcements back in September mentioning you wanted to increase the amount of like formal mathematical code in existence by 2 to 3 orders of magnitude. We're talking about like the risk of bugs. Mathlib already has like 1.5 million lines of code.
Which is tiny.
What? Say it again.
Which is tiny.
Yeah.
I
Well,
mean, 1.5 million lines of code is nothing, I mean, compared to current code, even
well,
like simple projects like.
Well, so are you claiming 150 plus million lines of verified lean in like a year then? And what's the bottleneck, right? Like, is it generation speed or like proof search or like the
I
availability?
think at this point it's getting more and more. I mean, human is still a bottleneck because not every, so it's, our formalization systems are not 100% automatic, especially when it comes to formalizing definitions and theories like from scratch. And humans typically have to check that the definitions are correct. I mean, it's getting better and better, and we have more and more automated ways of verifying it, but it's still a bit like problematic. The second problem I see is compute cost, and this formalization effort cost a lot of money, and they had to go down in cost in order to achieve the 100x like more verified math. And the third problem I think is collaboration. So basically we don't have so they have a lot of isolated efforts, but they are isolated and they don't build on top of each other. So we have to have an environment in which these agents or companies can collaborate and then build the overall building of mathematics, not just like individual towers everywhere.
So, like, I know a lot about verification and things like that. So, like, describe me, like, what is the actual work? Like, you create a lot of like proofs and then try to validate them.
Yeah, that's one aspect. But in general, so as I think I already mentioned 2 goals. So one goal is that what you said right now is that if we prove something completely new, like AI comes here and say, okay, I proved the ABC conjecture or whatever. I mean, some people like Mochizuki claims he did it, but many people don't believe it. But we could also check his proof if our systems get really good. And then we could find, okay, I mean, either we fail at some point, and then we can ask targetedly, okay, we could prove this, and this, but here our formalizer just gets stuck, and can you help us? And then we could avoid this kind of controversies in mathematics. But I think the real goal is not really like clearing a few controversial statements. It's much more about like mathematics. So all these AI agents will be extremely powerful within a year or even half a year. So they will be better than any human, and then we will start creating mathematics that basically solutions to a lot of problems that were never look like possible before, but we will not be able to verify those. How do you verify that amount of mathematics if you produce like a lot of like English language mathematics? Then you can ask an AI to check it, but do you trust that AI that checks those statements? I mean, or that proofs? I mean, I wouldn't. I don't think that AIs are trustworthy in that respect of saying, okay, I went through this proof and I think this proof is correct. And then we say, okay, hooray, we have this proof. So I don't think that works. I really think we need a formal mathematical proof that we can check without AI, and then we can say, yeah, okay, now it works. And the other thing is that I think this formalization will become basically like basically like a invisible machine language of all of reasoning everywhere. So it's basically just like the same way that you don't look at your assembly code typically where you write a program, even if it's a compiled program, but otherwise even so it's like same thing will be with Lead, that you in the background you always have these checks that everything is all right, everything is satisfying properties, everything, all my code is working, etc., or all my theorems are correct, but you only interact with natural language. You don't need to care about all that. A lot of lean and formal verification going in the background. Or a chip designer also doesn't care what's going inside the set solver. But I mean, that might be the source of this controversy, that people came like, okay, there was this controversy that Mathink was formalizing this sphere packing result, and then people came in with various problems that are saying, okay, I mean, what do we do with this result? I mean, we can accept it as like all that code, but that code is not very nice, and we cannot build on it because it's a code generated not for humans. It's kind of like similar than if you write a C code and then you compile it to assembler and give it an assembler programmer that, okay, now you have to develop, you have to build upon this assembler code. And then, of course, those programmers would be upset because they say, okay, I mean, I don't want to extend a C compiled assembler because I have no idea what it's doing or how it is doing. So it's very, very artificial. And then, so there is these two schools, this old school formalizers who's formalized because they like this nice formalized proofs that they cannot. So it's basically an artisan work. And then there is the vision that you generate all these formal proofs and nobody wants to, but we don't care that anybody looks at them. That's not their purpose. And I'm in the later camp. I don't really care about the beauty or whatever of those limp loops. For me, it could be a completely different logic or whatever. It could be a very messy first order logic proof. I would be just as happy with it. But other people, they are in the camp of like, yeah, it's our garden, this nice garden of all these super nicely written formal proofs, and we just tending to this garden and growing these proofs here. Yeah.
And do you think like we can use it to, like, for example, chain of thought, right? Like all these like discussion about like, does it useful, or like can we use this like kind of output of the model that blurb like about something that we don't really know? Like, do you think we can use like, I don't know, like in the optimal use case we can have actually some verification process of this output?
I mean, I don't understand. So what verification process do you want?
So I don't know, I want, like, for example, like if you say that like in math, right, in math we are doing some verification for like we verify the solution, right? We verify the process, and this gives us some guarantee about the solution. Do you think we can generalize it to other cases, that like we can have some guarantees about the solution based on the intermediate steps of the process? For example, in I don't know, in biology, right? Like if we know like that, like if we can have like ask a model like what is the final solution to some like reaction, like we can have, we can check it, right? We can check like the intermediate reactions, and if we have a good understanding of these reactions, we can verify it, right?
Yeah.
So do you think this verification of the intermediate steps, this is something that we can use in other places? Or you say like math is very unique in this sense that like we know all of it, we know how to decompose it, so we can
Yeah.
use an
I mean,
abstractly to.
as mentioned earlier, I'm very, very, very bullish about mathematizing a lot of subject that looks very hard to mathematize. Because basically AI will make our mathematical abilities so strong that you will be able to capture mathematical statements that are much less clear-cut than previously. So for example, you will be argue, so if AI helps us to discover certain statistical or probability, theoretical stuff about how uh, like quantum mechanics works, or like how molecule works or chemistry works, or then we can basically we will be able to have a lot of like maybe not 100% logical evaluation, but very strong statistical bounds on what is the probability that something went wrong. So for example, like if you do protein folding, it's not clear that your protein has the absolute minimum energy, that it's really the way it will fold. But mathematically, you could prove certain lower bounds and they say, okay, I'm only this far away from optimum. And then also the question would be, is there any other like structure that folds similarly? And this can be captured. So basically, AI will be able to create guarantees that can be captured with very sophisticated mathematics, and then that mathematics could be verified with verifiers. And I'm very bullish about these things because this is almost impossible for humans, but for AI this might be, or it will. I think it will be possible. It just we need to we need to accept that AI is so much more powerful in mathematics that we actually aim for these kind of applications. Because a lot of people are just not really seeing the potential of mathematics in these domains, because they say, okay, this like chemistry or biology, it's very, very fuzzy and we don't really know the rules. And that's true, but it's us. It's not the... so we already discovered a lot of new things in the past decades. But it's like humans are slow, and it takes a very, very long time to come up with these things. But AI will be much, much faster.
But you think there is a trade-off, for example, like I worked in the past on theory for AI, like to prove like what does it mean, the intermediate level, thing like that, or compression. At the end, you have a very fundamental trade-off between how much you can formalize it in a rigorous way, like to practice in real world, like how the actual models are working, and what you can assume about them. So, do you think this is also true for this case? There is like a trade-off between rigorous and like to be like very I don't know, formal methods to do math, and models, LLMs that you can scale to I don't know, billions of models of parameters.
So I think the number of parameters, the increase of parameters might be a good thing for mathematization, because you can look at limits. Okay. If you have like very large structure, you often get like a simpler statement and then if you look at smaller structures. But so yeah, I mean, I think you are raising multiple questions in one question. So one idea is that, so for example, when we think theoretically about AI, then we often don't apply the exact same mathematical output to create the AI as we. So if we are using mathematics to build an intuition, and then we just say we approximately apply that intuition and see whether it has at least any correlation with the real world behavior. And I think that's already possible, because that's a kind of like within the human So basically, even within human abilities. So we can do that. We always analyze things mathematically, and at some point it breaks down, and I say, okay, we give up, but at least it gives us an idea of what to design or how to run this or what to. So almost all the optimizers that were designed in the past years, they had a mathematical idea in them, but they're not. Whatever you prove, it's not really proving that actually your optimizer will be better than the other. Or when you have like something like this, this assumption, new attention mechanism like the latest one, where you are just trying to remove the redundancies from the attention. That also has a mathematical idea in it, that there are correlations here and it's not efficient and whatever, and then we remove the correlations and then you try it and it works, and then you don't prove that it works, but it's at least the mathematics gave some idea of how to improve things, and then if you try it out, and the AI will do the same thing. So that's why it's important for the AI not just try random stuff and say, okay, here is a new attention mechanism. I don't know why, but it's like it's probably better. The other thing I think will be important is that you actually will be able to find like prove real things about AI that you cannot prove today because it's just so complicated. And then the AI will be able to analyze your network completely for numerical analysis, like floating point inaccuracies, or maybe even like how you write on certain things. So there are a lot of like extremely unintuitive, subtle details in what you write and that how it turns out in reality. So, for example, in floating point addition, not even associative or whatever. So it matters how you add up things or how you do even the basic operations. It can make or break your model, and AI can think about all these things and make sure that you whatever has to cancel out cancels out, or on average you get the right things. And it can analyze these things, and it will be able to analyze 1,000 times more things than we can as humans, because when you do it today's age, where you have like 1 month to come out with a paper, and then somebody scoops you in the meantime. If you don't do it, then you cannot do like a lot of analysis. Just like come up with an idea, quickly implement it, works, okay, actually write a paper, that's it. But AI will be much more thorough than that.
So related to this, if Gauss can formalize field metal proofs, can it eventually formalize software correctness proofs? And so I guess my real question is like, is Mathematics Incorporated secretly a program verification company?
I mean, not secretly. It was in the charter, so that was one of our goals, is to create verified superintelligence, and that applies to programming next, and then science is later. So yeah, but I'm saying it's basically what I said about like AI, mathematics for AI. It applies to any other program as well. So, but AI is a particularly useful application because it uses a lot of math directly. So, of course, it's a good idea to use AI for AI, especially mathematical AI for AI. But I mean, other code, definitely. So I think that's what I said before, that we want to move toward verified software. And I think since a lot of software, the most interesting softwares have some mathematical tricks in them, or they talk some complicated logic. For example, if you look at all the like these various like protocols, you have to verify that the protocols are safe in some way or the other. So they are mathematical statements about not having certain situation arising. So even whatever the players do adversarially. And you want to verify protocols, you want to verify numerics, you want to verify memory behavior, algorithmic behavior, like is this really like consuming not too much memory, so it's a linear memory use, for example, or all these things. And it could be, so AI needs mathematics for that. For example, if you want to like hard code like a simple big O analysis into programming language, several people tried it like earlier into 2000, like making a programming language so that we are tracking the asymptotic behavior of programs. But they mostly failed because it's like most of the behavior depends on actual more fine-grained behavior of the program. So it's not like you can track it easily with a with a simple type system. So therefore we need like real mathematical analysis, and big-O notation requires an understanding of what is an algorithm, what is a asymptotic, what is a limit, what does it mean to function to be asymptotically similar, or one dominating the other. All these things. This is a mathematics. This is a calculus. This is algebra. Whatever. This is all you need, and then you need basically a big foundation for all those stuff. So in order to analyze code, we will need a very firm mathematical foundation on which you can do that. And you don't want to hand code all these things. It will fail, but AI can do it.
And then I'm curious then also, just going back to kind of, you alluded to your like foundational deep learning work that you've done in the past. You did batch normalization right back in 2015. And it has like so many citations now, right? 45,000 plus. And I think its original explanation was around reducing internal covariate shift. But it's been challenged by some other work, which suggests that, like, for example, that it smooths the loss landscape. Do you accept some of this like subsequent work that kind of offered revised explanations?
So yeah, generally, so just to give a very candid view on what happened is basically, I was thinking of this benchmark idea before, like this paper, for 2 years. And then when I met Sergey, he was already implementing his own version without completely independently. And he was proposing this covariate shift idea, and he wrote in the paper, and I was saying, sure. I didn't completely understand it, to be honest. So I'm always extremely skeptical of any theoretical results of being presented as an ultimate truth.
So
So
why you think?
Hmm?
Why you think does it work?
So I had a very simple original motivation for doing similar to. So I was thinking of that for a long time, around the time that Dropout came out, and I was saying of something. Typically, it's a no-brainer that if you want. At the back at that time, it was a no-brainer that if you want your network to work well, then you want it to normalize its inputs. So it's basically, and I said, okay, why not normalize the inputs everywhere? It's like every layer, every output of every layer is the input of the rest of the network. so, so if it works on the first layer, then basically the rest of the network has to have also a normalized input. But there is other explanation that's saying like you want to have the your activations in the range that's kind of like the most sensitive range for your function. So basically you don't want them to be like very far away, because then if like activations go too far from each other, then they cannot be like. So one will dominate the other, and then the other will not play any role anymore. The other reason is that so basically there are a lot of reasons of why normalization is a good idea in general, and that was the main motivation. And it was like a completely no-brainer to me that you typically optimize your input, and it has a huge effect of like normalizing your input activations.
But so, do you think it's actually necessary? Because like we talked with Zhang Liao from Princeton, right? And they published a recent paper about layer-free normalization.
What normalization?
They basically they use like a sigmoid or like tangent symbolic function instead of normalization, and they learn like the slope of it. Do you think it's necessary, or like this is something that just
The slope of the sigmoid. So I don't know that paper. I might say something completely stupid here.
No, but
the
like
slope of the things are basically like constant multipliers before the so they are kind of like normalizations. So yeah, so back to
but
your
do you think? Okay, continue. So yeah.
your original question was, is it necessary? And I say no. batch normalization, I think, is a convenience tool that if you don't know the right hyperparameters, you in certain circumstances for certain networks like convolutional networks especially, batch norm is helping you to extend the set of hyperparameters for which your model will work well. So you have less luck. I don't think it's necessary. It's like if you have the exact right hyperparameters, you typically don't need batch norm.
What do you think is necessary for current AI models? Like, what are the fundamental parts there? Or maybe there
What do you
aren't.
mean? I don't get
Like,
it.
do you think, okay, so, like, do you think now if we will replace a transformer with other architecture, like, I don't know, whatever, Mamba or
Celestia.
something like that? Or do you think if we now, like, replace, like, if we will change the data or, like, the training algorithm, like, do you think there is something fundamental that we actually we must have in order to train good AI models?
I mean, we have like reasonably good AI models already, and it typically it never works without good data or good optimizer or good network and good normalization. I mean, transformers need a lot of normalization, not batch normalization, but I mean, several kind of normalizations work, but batch norm is not the most appropriate for them. But yeah, I mean, there are results that you can avoid all these normalizations if you do other stuff, but um, it's not, I don't think, so I mean, I think data is absolutely critical to get right. And all the others like normalization or infrastructure or like architecture is somewhat secondary. Of course, if you are too far away from so there are a lot of different architectures that can work pretty well. And they don't need to be, I mean, we do LLMs because that we have like in 3-4 years of tuning of various components. Like we have like insanely high tuned attention mechanisms and like all the research of how to manipulate them or normalize or decorrelate or whatever. And then we have like mixture of experts that are also very, very well studied, that they help you to use less memory during inference. And we have KV caches and all these things are created. So we have a huge infrastructure for LLMs that like transformer-based LLMs where we just built it up. It's basically this similar to the hardware lottery. We have the infrastructure lottery that is very hard to create a new infra from scratch that competes with it. It's not because other infrastructures might be much better. I'm 100% convinced that transformers will not be the main workhorse in 5 years. Let's think it will be something that AI will design or develop or invent from scratch, and it will be much better than transformers.
So speaking of predictions in time, I think that there was a Twitter thread where you revised your superhuman AI mathematician timeline from 2029 to 2026.
Yeah.
You think that we will achieve that this year? And specifically, like, what specific capability would a system need to demonstrate for you to declare the milestone achieved?
Okay, so I mean, I had some very clear, I think it's like, I mean, clear to me, guidelines. So basically, when I revised, so I mean, my original, when I revised myself, I revised from 2029 to 2027. So that was basically the original thing. And then I had like a discussion with François, like 2022, and he was said that, yeah, let's bet. And I say, okay, let's bet on 2027. And he said that, I mean, you have, I mean, yeah, I'm not so certain about that. And then he proposed, let's do 2026, like June, which is we had a paper together with François 10 years ago. So that will be the 10 years anniversary of our deep math paper for 2016. And then I said, okay, sure, let's bet. So, I mean, I'm not really sure if it's, so the criterions, let's put it, so first of all, the criterions that I suggested that we will formalize, I think 10 or 100 textbooks completely autonomously, and we will see AIs completely autonomously created AI proofs on on at least 10 conjectures in 10 different areas of mathematics that were attacked by humans for at least a decade or longer. So I didn't suggest that we will see like any Millennium Prize problems solved this year or next year even. I don't really know anything about, maybe it will take 100 years even for AI to prove P n equal NP if ever. But I mean, these things are singular and they don't really know how hard they are. But I think it's like what we can see already is that the formalization abilities go up exponentially. Like we will see, I think, 10 books easily, but even hundreds by this summer, formalized completely autonomously. And we will see a lot more. So we already seen several like not too hard statements, but still frontier statements that have been open for years solved by AI, and I think it will accelerate. So we are very, very close to to that point what I suggested like 5 years ago.
What are the missing parts?
I mean, but I don't know if it's missing. It's more like, is the capabilities, how far is it really like can do anything that mathematicians can do? And I mean, I think that this year we will not be like we will not see an AI by this summer or whatever, or September, that is as good as a Fields medalist, but it will be like a very strong working mathematician level, like top 10% time. And I mean, what we need is basically, I think, is verification, or better verification, but a lot of companies are working on and people working on that, or universities. And also because, I mean, it doesn't matter if you prove a hard problem if you cannot verify that the solution is correct, right? So that's why we need formalization. And then the other thing we need is like a much bigger repository of formalized mathematics, because you cannot really formalize things if you didn't formalize the necessary ingredients.
And we've talked a lot about like Lean, mathematical formalization, like proof assistant. Are there any other proof assistants that you're very interested in for all of this mathematical formalism? I've heard of, I'm really not an expert on the field, so I don't know the quirks of the ecosystem, but I've heard of Coq and some others. What's your take on all of these?
I mean, generally, I mean, even in the last years I worked at Google, and Lean was already big. I didn't work on Lean because I thought that AI doesn't need the same level of niceness of the Lean is very nice for humans, but for AI it's okay. So if your language is strong enough, like Coq is strong enough and HOL Light is strong enough, these are all higher logic systems. So you don't really need even first order logic would suffice. So you don't really need Lean or any of them. You just need one of them. So I mean, you don't want to build up like 10 different repositories for all of them. It's like I think it was Linus who told once that the good thing about standards is that there are so many of them, or something like that. So it's basically, the problem is that you don't really need like 10 different programming languages for the same purpose. So especially if you don't have to write them manually, if you don't have to write them as a human. So for example, Rust is nice, but if you would have C++ plus formal verification, then who cares whether your AI writes C++ or Rust? I mean, I don't. It's like Rust is a nicer language than C++, but I mean, I still fine. I mean, if it verifies me everything with guarantees, with a proof checker, then I don't care.
Well, there's concerns about like who has the most training data in a particular language, and it's also about like token efficiency.
Yeah. I mean, so that's a very good point. So one of the reasons that I work on Lean now, and almost everybody, is that Lean has most human data. That basically that most code was written in Lean, most formalization currently. And that basically shifted the tides of saying, okay, previously there were a lot of projects and all of them had similar data, but now Lean has more data than all of the others. So naturally, person, you go where the data is and okay, let's use Lean. But if you start doing reinforcement learning loop and generate a lot of proofs from scratch, then you wouldn't care. It's like, okay, then you start doing RL, and then you do address all of mathematics and generate all these statements completely automatically. Then basically like MetaMask would do, or whatever, even the crappiest formalization would do.
And so I have a question about like math in general. So like, do you think so right now that we can essentially formalize everything, or almost can formalize everything, and agents can go and prove exponentially many theorems, right? And we can able to check them automatically in the near future, right? Um, what do you think the role of mathematicians will be? Like, what they have actually to, what they can do after it? Do you think we will see no more mathematicians anymore,
So I
or
think
something
in the
different?
next 5 to 10 years, we probably see like so the role of mathematicians will shift more towards like giving so basically the direction of which areas to explore. Uh, but so basically telling the AI that, okay, I want to see like develop a theory for this or that theory for that, and then basically iterating with AI on various of these things. I'm not sure if that role will go on forever, but I think for the next 5 years probably will. Also, I think mathematicians have a lot of other roles like teaching, and then I don't really. I mean, I think AI can be a very helpful like help to educate people, but I wish, I mean, I have like kids too, and I don't really wish that they will be exclusively taught by AIs. So I started a company in Hungary that is more for AI augmented education, and the goal is to create a system where teachers are augmented with AI, whether they can do the right thing. So basically, they could give the inspiration, the human touch, everything. So basically, what the teacher should do, but they don't need to do a lot of the boring work like grading or setting up problems and figuring so or creating the curriculum. All that can be done by AI, but the teacher should be there as a role model for the student. So I think humans, just like humans, it's like that's our nature, is that we want to be with humans and we get excited by humans. And if you look at chess, for example, then I mean, chess is not dead. It's like it became kind of like a soap opera, but uh, still, there is the skill is also there. So it's like people like skillful people, if they are, even if they are much worse than any AI. Uh,
But do you
so
think like chess competitions are between humans, right? Like we don't see, I don't know, mathematicians that are compete with other mathematicians. Do you think
a
like
lot of the history of mathematics was that like cassading with Cardano and whatever, even Pythagoras. I think it's like they were challenging each other and trying to like Newton and Leibniz or whatever. So they did a lot of these challenges to each other. That's I can do this, can you do that too? And then uh, so I think that there's a much more human element to mathematics than most people know. But I think this puzzle solving effect of like saying we are putting it on a pedestal, that this person is so much better at problems. Maybe we'll still do it, but I think it will be very strange for mathematics. I don't really know how it will work, but I think it is kind of like another analogy that I like to say, that I mean, when astronomy, before the invention of the telescope, you had to look at the sky by your natural eyes. So it's like you needed very good eyes to be an astronomer, because otherwise you couldn't see the stars or the planets. And then there were this clear limits of how much you can do that way. And then the telescope came by, and then people like okay, we don't care anymore, so we can just like, and it becomes more like a theoretical work. And I think that similarly, like mathematics, is we have this telescope that can look into the mathematical universe much more deeply than any human mind can, and we can decide what we do with that. So I think it will be. So mathematicians will need to adapt, but they typically still in denial. But I mean, I think that most of them are kind of excited that they can learn suddenly. It's kind of like coming to dying, and then you come to heaven, and suddenly you can learn a lot of, so, okay, how this works, and then God explains to you. And it's like uh,
they
that's
they
the
can
dream of a
implement.
scientist, a religious scientist, that I die and then I can learn everything.
Now when they retire, they have time to put time in all the other things that they
I mean, it's
wanted.
up to us what we do with the AI, but I think, I mean, I'm very concerned about AI's potential general. I don't really think that humans need artificial work. So it's like, that's why I'm kind of like, I'm not that worried about that. My worry is whether the benefits of AI will be distributed in a way that nobody is left behind. So that's an important problem. And the other problem is, of course, AI could be like completely disastrous, like just like Terminators killing everybody. I think that's a very realistic outcome. And then we can like other even crazier outcomes that I also believe somewhat realistic. So yeah, I think I mean I'm not super optimistic, but so that's why I'm also kind of thinking about these problems. And I think verification could play a role to some extent of making AI be more honest and not cheating us.
So, I related to like what humans' role is in, as AI gets better. I'm influenced by how in chess it took 5 to 10 years after Deep Blue comes out for AI to become so much better, chess engines at that point, that even grandmasters trying to help AI like centaurs were worse than the AI models alone. But at the same time, I'm also influenced by the fact that chess is probably the biggest it's ever been. And it seems like most people who are sufficiently using AI right now are the busiest they've ever been. So I'm wondering if Jevons paradox outweighs. And so what's your take on like, do you think that there's like a job apocalypse, or are we all going to work harder than ever and the work explosion, or I don't know.
So these are very exciting questions. I think a lot about it. And I mean, so I think I made several predictions like this about mathematics. And also I made another prediction like 5 years ago about RKGI benchmark, where I had like discussed with François, and I just lost it by a month. But yeah, I think my track record is fairly good in these predictions, but I started to be like very honest to myself. Then I think we reached that point where it's like there is a event horizon for me, at least in the next 2 years. Maybe for the next year I can make predictions, but not more than 2 years. So I think it's like the potential if AI is getting to that level that is basically any thinking of like any projections or whatever I do is like lost in these nonlinear effects of AI on the whole society. So I think, so what I'm most concerned about is that we have a lot of different options, that it's like it depends on us of how do we deal with that. And I distrust humanity more than I distrust AI. Actually, I think we don't have a good track record of making taking care of everybody in the to the effect that we could. So basically, humanity is a mess, and we uh, yeah, and now we are at a point in history where we should get our we we would need to be better than that, but it doesn't look like we are getting any better. So I think it's like it could be very sad. We could use AI to basically enslave humanity, or we could use AI to create dictatorships and surveillance everybody, or we could use AI to have like build huge robot armies. And I think that's, unfortunately, that's something is happening. And I mean, I think humanity could have a super bright future, but I think we might destroy it.
Okay, we almost out of time, and there are several questions on social media. We answered some of them, so let's see. Okay, what should students who work in this field focus on if companies like Mathin can do large-scale auto formalizations?
I mean, if you do manual formalization efforts, I would say, I mean, you do it for your fun, maybe, but not because it's a good career path. I don't really understand the question in terms of like, I think, so basically, I don't know but how general this question is. I mean, it depends on the scope of the question. So if it just applies to formalization, I definitely would say don't do artisan formalizations if you don't. If you don't have fun with it and just you want to like solve Sudoku puzzles or whatever, that's similar level. But if you generally ask about mathematics of what a mathematics student should do, I still think one should rethink their career choices or life choices or whatever, and try to embrace AI and then have fun with AI and then figure out how to use it best, how to leverage AI best. So I think it's like the traditional work passes or career passes. I think they will be over very soon, and the most important skill set will be how well you are working with other humans and how well you work with other AIs.
Okay. Another question is like, do you think it's possible to formally verify alignment properties of a model, or are they fundamentally too informal for formal systems?
Yeah, I think we can. So I think you cannot 100% verify alignment. So alignment, I like the word validation better. So validation means that if you give some task to an AI, then you make sure that the AI's formalization of that task, like saying it transforms, for example, in mathematics, you take an informal statement, you transform it to a formal statement, and then whether the two are in alignment, whether the formal statement actually, if you prove the formal statement, would it count as a proof for the informal statement, for example, or you create an algorithm based on a definition, then would your algorithm actually, the formal algorithm would do the same thing as your informal specification said. And I think we could improve validation a lot, but it's inherently impossible to make it like 100% certain, because that's the whole point of informal, is that it's not 100% specified, so you cannot make it 100% certain that the human meant what is done. And there are a lot of other issues that, for example, Eliezer raised, like for example, what happens if your AI solves the task you told it to solve, but in the meantime it kills humanity, for example, or whatever. It does a lot of other harm, like boils down all the water from a river or stuff like that. And these are much harder questions, and the problem, you cannot specify all the harms that an AI could do, so it's very hard to verify formally whether your AI doesn't do all the harm that could be bad.
Okay, yeah, I think we're out of time. Do you have anything else that you want to add, to promote, to sell?
Oh no,
Okay, so Christian, thank you so much for coming. It was a real pleasure.
it was
And
my pleasure. Yeah,
thank you so much. And Ellen, thank you.
Yeah,
thank
it's
you
a
very much.
pleasure to be here and to get to ask these questions to somebody so legendary.
Thank you very much.
Thank you so much.
Have a great day. Bye.